Hello. In previous videos I have discussed the sample mean, which is computed using the expression shown on this slide. I have explained that because this quantity is computed by adding together identical random variables, it is itself a random variable. I have further shown that the expectation of the sample mean is equal to the expectation of the identical random variables from which it was computed. Lastly, if the random variables are also all independent, we can write the following expression for the variance of the sample mean. The variance of the sample mean is simply the variance of the underlying random variables divided by n. I mention all this here because the aim in this video is to determine if we can derive similar expressions for the expectation and variance of the weighted mean that is calculated using the expression shown on this slide. In this video, we will assume that all the xi are identical random variables. The wi, meanwhile, will be fixed parameters. In other words, we are assuming that these quantities are not random. With an understanding of what we are computing, let's see if we can thus derive an expression for the expectation of the weighted mean. In doing so, we are obviously calculating the following expectation. By recalling that the expectation is a linear operator and remembering that the wi values are all non-random parameters, we can immediately see that this simplifies to the following. We then note that all the random variables are identical and thus have the same value for the expectation. The expectation can thus be brought outside of the sum in the numerator as shown here. The sums over all the wi in the numerator and denominator then cancel, and we find that the expectation of the weighted mean is the same as the expectation of the random variable from which it was computed. Having determined the expectation of the weighted mean, let's move on to the variance of this quantity. This is obviously computed using the expression shown at the top of this slide. Furthermore, we can make some progress by recalling that we have just learned that the expectation of the weighted mean is equal to the expectation of x. The second term here thus simplifies to e of x squared, and we can rewrite what we are being asked to calculate as shown here. Let's focus now on what we are taking the expectation of in this first term here. If we write out the square of the sum in the numerator explicitly, this perhaps makes things appear more straightforward. To make multiplying out the brackets really easy, let's represent the process of doing this by drawing a table in which the title of each row is a term from the first bracket, and the title of each column is a term from the second bracket as shown here. The process of multiplying out the bracket now just involves filling each element of the table by multiplying the title of the row by the title of the column as shown here. The expansion of the two brackets is a linear combination of all the terms in this table. We can thus take the expectation of this table and exploit the linearity of the expectation operator and compute the expectation of each term in the table separately. If we start with this element, we can make progress by remembering that w1 is a fixed parameter that is not random. We can thus bring the w1 squared outside of the expectation as shown here. We then remember that all the random variables are samples from the same distribution. They're all samples for the distribution for the random variable x, so the expectation of x1 is equal to the expectation of x. And similarly, the expectation of x1 squared is equal to the expectation of x squared. We can do a similar set of operations for all of the terms on the diagonal. We can thus work out that the contribution of all the diagonal elements is given by the following summation. Let's now turn to the off-diagonal elements. We once again do not need to include the weights inside the expectation operator as these are non-random constants. Furthermore, we have assumed that the random variables are independent, so we can replace the expectation of the product of the random variables with the product of the expectations, as shown here. The random variables are also identical, however, so we can replace the expectation of x1 times the expectation of x2 with the expectation of x squared. We can once again perform a similar treatment for all of the off-diagonal elements in the table. The total contribution of these off-diagonal terms to the final expectation is thus given by the expression at the bottom of the slide. If you want to determine where the term in brackets comes from, use a table like the one shown on this slide to write out what the square of the sum of the weights is equal to. You should then subtract all the diagonal elements in the table so that only the off-diagonal elements remain. To summarise the results from the previous slide then, we have arrived at the following expression for the variance. Notice that if we split this into three separate quotients, the factors of the sum of all weights in the second quotient cancel. The two squares of the expectation thus cancel, and one is left with the following expression. The expectation of x squared minus the expectation of x all squared here is just the variance of x, however. So the final result is that the variance of the weighted mean is given by the following. To conclude then, we have in this video explored the properties of the weighted mean that is computed using this expression. The xi on the right-hand side is a random variable, as is the final quantity xw. Importantly, however, the wi values are not random variables, they are constant parameters. We have shown that if all the xi are identical random variables, then the expectation of the weighted mean is equal to the expectation of the random variables from which the weighted mean was computed. In addition, if the random variables the weighted mean is computed from are also independent, then the variance of the weighted mean can be computed from the variance of the random variable that was used to calculate the weighted mean. And this is done using the expression shown here. I hope this was useful. Thank you for your attention.